Hi, thanks for listening to my talk. My name is Moghimi and I'm a PhD student at Worcester Polytechnic Institute. Today I'm going to talk about my work on side channel attacks. In TPM-Fail, we found multiple vulnerabilities that exposed crypto keys from trusted platform module. This is a joint work with Berk, Sunar, Thomas Eisenbarth, and Nadia Heninger. TPMs are security chips that are connected to our computers. You can find them on your laptop, your desktop workstation, or even on your mobile phone. TPMs are supposed to be tamper resistant and side channel resistant, which means you should not be able to steal crypto keys from these devices by doing side channel analysis. We use TPMs because we cannot rely on the software stack to protect these crypto keys and credentials. So we put them inside this TPM chip and assume everything outside of this is untrusted. TPM support a wide variety of crypto functionalities, but more importantly, they support digital signatures. And these digital signatures, of course, are important nowadays. They are used everywhere in the internet. And thanks to more recent software libraries like OpenSSL or the software stack in Windows and Linux operating system, we can use these TPMs to perform digital signatures. As a result, the private key of this digital signature is kept secure inside this TPM vault. Since TPM version 2 now, Trusted Platform Module supports digital signatures based on elliptic curves, and that include ECDSA, ECSchnorr, and ECDAA. The Trusted Computing Group also expect manufacturers to have some security guarantees for implementing the security chips. And according to their website, they expect vendors to demonstrate successful common criteria certification at level EAL4+ moderate. And we can see a list of these devices that have proper certification on their website. For example, we looked at one of these devices that we studied it in this paper, and this device in the datasheet and the CC certification that we could find on the internet, they clearly claim that this device is supposed to be resistant against side channel attacks like timing attack. So the question is, are these devices actually secure against side channel attacks? So one of the interesting class of side channel attacks are timing attacks, as they are not intrusive and we don't need a special equipment to perform these attacks. And if a device is vulnerable, sometimes also you can do timing attacks remotely. For proper timing analysis of TPMs, we wanted high resolution timer, so we figured that it's a good idea to use the CPU cycle count as a timing resource. And why is that the case? Well, the TPM that is connected to our computer, whether it's a dedicated TPM or a firmware-based TPM, it generally runs 100 times slower than the CPU. So the CPU cycle count here can serve as a high resolution timing resource with almost nanoseconds resolution. Initially, I did some tests on a TPM technology called Intel PTT. Intel PTT is basically a firmware-based TPM that runs as part of Intel Management Engine. Intel Management Engine has its own low-powered microprocessor, but it's located in the same DIME as the CPU. Here, for instance, we can see the figure for some timing analysis of this Intel PTT by just measuring the CPU cycle count from the user space. And we realized that during the ECDSA signature generation, some of the signatures are generated faster. And here, the signatures on the left side of this histogram are generated faster. So this kind of gave us the intuition that we should build a tool to do this timing measurement even more precisely. So we implement a kernel module that modifies the behavior of the TPM kernel stack on Linux to perform this timing measurement as close as possible to the MMIO interface that talk to this device. And with this tool, we realized that these timing samples we collected actually has a symmetric behavior where we have different brackets, and in each bracket we have about 4 times more samples compared to the next one in the figure. So this already gave us the intuition that this leakage has to have to do something with the nonce. We looked more closely to this. If you look at the ECDSA signature operation here, we can see that by the knowledge of the private key, we can basically reveal the nonce. So we programmed one of these TPM devices with a known private key, and we started collecting signatures, and we revealed the nonce for each of those signatures. And we realized that for every additional 4-bit of leading 0-bit in the nonce, we can actually see a faster signature generation. And for example, for 12 bit of 0 in the most significant bit of the nonce, we can see that the signature generation is about more than 3 milliseconds faster. So we looked at also some other TPM devices, and we tested a bunch of laptops and desktop computers we had in the lab. And some of these devices, they were using the same Intel PTT technology, but some of them, they had their own dedicated trusted platform module. So with the trusted platform module, with the dedicated ones, we actually found that another one also has similar vulnerabilities. And here, if we look at the histogram for ECDSA signatures that we generated on a STMicroelectronic TPM device, we see that the Gaussian distribution is not fully uniform here, even though it doesn't have an obvious pattern like Intel fTPM. And similarly, we looked at the nonce for the signatures that generated by this device and realized that there is a similar vulnerability here. But instead of for every 4 bit, we see for every additional 1 bit of 0 bit in the most significant bit, we see that the signature is generated faster. You can also see that there is a direct correlation with the bit length and the timing, and this correlation is linear. So far, we just have some partial information about the bit length of the nonce. What can we do with this? We systematically perform an attack which started collecting signatures from the TPM device that is programmed with an unknown private key. Then we filter those signatures that have a known bias, and we filter those signatures based on a template that we know already, because we discovered these vulnerabilities. We know that the signatures that are generated with this timing threshold, they have a known bias in their nonce. So after filtering the signature, then we can feed these signatures that have a bias to a lattice-based key recovery algorithm to recover the private key from the TPM. So how does this lattice-based attack work? Not going to get to the detail, but the main idea is that if we rewrite the equation, the ECDSA equation, to a simpler form, we can have a simple equation with some noun values that are labeled at A and B, and the secret values in this equation is the nonce KI and the private key that are labeled as red. And without side channel information, we cannot really recover any of these private values here, because we have one equation and two unknowns. But with the help of the side channel information, we can actually have some more information about the nonce here. And the information here tells us that the value of the nonce cannot be bigger than a certain limit, and that limit here is defined as the variable x. So this problem, this exact problem, is known as an instance of the hidden number problem. And there is a technique based on lattices that can recover the private key from this nonce with polynomial time. And these lattices and lattice attacks have been studied for a long time by mathematicians, but we can use the same technique here actually to recover the private key. So we constructed a lattice here in the matrix that we see that in the figure. We can see the exact definition of the lattice we used, and when you fill up this lattice with biased signatures and you feed this to an algorithm called LLL, this magically can recover the private key for us. So we did some true analysis of this attack with different number of signatures and parameters. And here we see some of the results in this figure. And we tried with different lattice dimensions and different number of signatures. And the end result is that on the Intel fTPM case, we can recover the private key with like maybe 1,200 signatures. And generally, generating these signatures maybe takes 3 to 4 minutes. And for STMicroelectronics, we needed more number of signatures. In our simple attack that we tested, you need about 40,000 signatures, but some other people later on, they looked at the data set we put out on the internet, and they show that you can even recover the private key with less number of signatures by doing some other subsampling and improvement on the lattice attack. So we saw that we can steal this private key, and this is great because this TPM device, these TPMs, they are supposed to be secure even against physical attackers, and some of them, they even have a security certificate that says this is not vulnerable to such an attack. So now the question is, can we also do these attacks over the network? And if we look closer to the timing difference for each of those brackets in the figure for Intel fTPM, we see that each of those have about more than 1 millisecond timing difference. And on a local network, I can ping a computer on a local network with less than millisecond round trip time. So this gives us the intuition that these attacks should be possible also over a network. So in our paper, we demonstrate an attack on a local network on a real VPN application. So we configured the StrongSwan VPN solution according to their instruction to use a TPM for authentication. After we configured this StrongSwan VPN to use the TPM, this IKE protocol basically first DPL-man key exchange, and as part of this DPL-man key exchange, the client and the server would have a shared secret. But the second handshake is about the authentication, and that's where the VPN server asks the TPM to sign a message. But during the second handshake, we can just, as a malicious client, we can just measure the timing of this second operation, and we keep dropping the connection and again initiate another handshake. By repeating this operation and collecting lots of signatures, we could actually perform a similar attack as we mentioned before. And in this experiment, we actually realized that we needed 44,000 handshakes, which takes about 5 hours to have enough signatures that give us the signatures that we want, and we could recover the private key. And in this figure, we can see that with lattice dimension of 90, we can recover the private key with 60 to 70% success rate. So just a recap on our results that we also analyzed more thoroughly in the paper. The attack is successful for so many different scenarios, including system level adversary up to remote attacks. It's just the further you are from the device, your timing measurements have more noise, so you may need to collect more number of signatures. We reported these vulnerabilities to both of the vendors that they were attacked, and we also helped the STMicroelectronics to actually verify if their new TPM version is secure against this attack. I would be happy to take questions. Here are also some links to the website and the tool if anybody is interested to look at it.